had a test on Friday. I worked with Pathfinders all day yesterday, which doing the optics honor for them, which as an aside, it's ridiculous that they think in 2 hours you should be able to earn the optics honor. I mean, what are you really going to learn in 2 hours? Anyway. Well, it does, about 5%. Any questions you have about the test at this point? I didn't get them graded. I looked over them Friday because Chris got them to me right away. And then I don't think it'll take that long to grade, but I did not have time to sit down. I graded. Yeah, anyway. Any questions you had?
No, other than for some reason I blinked on evaluating integrals.
I think I had all the integral tables you needed though, right?
Yeah.
I figure I probably did because I don't remember them either, and I had to look at the tables to solve them. And I have a bunch of extra stuff that we'll use today, that you didn't need. The knowledge ones to me are actually more annoying. What is embarrassing is this one here. I forgot that the question didn't end here. I was telling Chris, they don't need a calculator because all they have to do is multiply two one-digit numbers and add them up and divide by 10. But it turns out that for the x squared part, you actually have to, do a square root. But if you left it in square root of something, I'd be fine with that. If you leave it square root of 0.79 meters squared, that's fine. I did notice that one person had a problem evaluating the integral for the expectation value position had L over 4 instead of L over 2. I looked at the graph and it had marked L over 4 for the expectation value. I'm like, what? And then I looked at the calculation. Well, that's what he calculated. He was true to himself. Well, clearly I'm not pointing at either of you here because you can't tell. I could be pointing directly at you and you wouldn't know which one I was pointing to.
It's like if it wasn't us, then we know it's the other guy.
That's true. I didn't do that. Did you do that? And that's not a major thing. If all of your process was right, that's not a huge concern to the grade.
The problem I had, if you go back to the expectation value, or the normalization, that's what it was.
Okay.
For normalizing when I evaluated, for some reason I didn't plug in the right values because I was thinking not 0 to L, I was thinking negative infinity to infinity for some reason.
Mm-hmm.
And that's why, for some reason, I was like, these numbers don't make sense.
Yeah. You're like, but it doesn't converge, right?
Yeah, exactly. So I was like, I put a question mark. I was like, this doesn't. But I wasn't thinking 0 to L for some reason.
Now that we had the first lecture on the particle box was just before that. I used the example here as the particle in the box solution to try to get us some familiarity. You can do these problems based on what we knew before, but now we're seeing this is how we got those. Right. So to the actual lecture, I'm going to get my integral table there ready so I can come to it when I need it. Because like I said, I don't have these integrals memorized either. Look, I fixed the Schrodinger equation. So we were doing the particle in the box, and the progress we made on Friday. Okay, it wasn't Friday, was it? I put Friday because I was thinking the last class period, but that was Wednesday. Is that we applied the Schrodinger equation in each of the three regions, and because of that potential being infinite, it turned out that it was the wave function was 0 in regions 1 and 3. It was only region 2, the region inside the box, where there's any chance of the particle being there. And so we had two ways of writing that. This way here was the general way of writing it. And then we had, I should make another highlighter. This way here was putting it in sinusoidal terms. And one of the things you have to ask yourself, it's not if you feel lucky, punk, but how do you know which one you want to use? Did that cross your mind at all when we were doing this on Wednesday? They're equivalent explanations, but sometimes you want to use one and sometimes you want to use the other.
Didn't cross my mind, but I guess it doesn't.
Yeah. Well, and the answer is so unfulfilling. You want to use the one that's going to be easiest for your problem. And now I ask you, how do you know which one's going to be easiest for your problem? For the particle in the box, there is a real simple way of doing that. For the particle in the box, you're saying the wave function needs to, we had the boundary conditions. I won't go there yet because, we had the boundary conditions that says that your wave function has to be continuous at each boundary. And for every problem except this one, you also have a second one that says the slope has to be continuous at each boundary. So the first derivative has to be continuous and the function has to be continuous. In this case, because we have an infinite potential, that's why our first derivative doesn't have to be continuous. But with that continuity and having 0 outside of the box, setting a sinusoid equal to 0 gives you nice specific angles and is fairly easy. Setting e to the ikx equal to 0 is not such a simple job. And so that's why in this case, it was easier to go to the sine and cosines. If we had something that wasn't equal to 0 at the boundary, I probably would have stuck with e to the ikx. So it's not a hard and cut clear science, but because I had equal to 0 at the boundaries, that's what made it easy for me to say, go to sine cosine. So now we applied the boundary conditions. We did first psi 1 at x equals 0 is equal to psi 2 at x equals 0. And so that would give us 0 equals, and notice I changed the names of my constants. I just thought it made more sense today. B cosine times cosine of 0 plus b sine times sine of 0. But sine of 0 is conveniently enough 0, whereas cosine of 0 is 1. So I have 0 is equal to bc, which was real convenient, right? The reason I want to use the sine cosine, boom, the cosine term disappears. And so then I'm left with just a sine function. So after applying that first boundary condition, I had psi 2 is just, and I'll just use b now since there's only one constant, times sine of kx. And then we went to the second boundary to say that psi 2 at x equals L is equal to psi 3 at x equals L. Thus, b sine of KL is equal to 0. And we had two options. We could say, hey, let's set b equal to 0. That's major fail. Why is that a major fail?
Then there's no wave function.
Bingo.
Like it's, yeah.
Then we said, no, we don't have a particle in a box. You lied. So we don't have the option of setting b equal to 0 or else we don't have a particle in a box. So then we have to say what condition would set KL equal to 0. And of course we do this using the radians as our units. And so we know that sine of n pi equals 0 for n equals any integer. That's true, right? We don't actually use n equals any integer because that gives us the condition that n pi is equal to KL, but K was square root of 2m e over h bar squared. And so the K was the positive sense on that, so the K has got to be positive. So I can't have a negative n. Furthermore, I can't have an n equal to 0 because if my n is equal to 0, I'm back to the situation of psi 2 is 0. And so while this statement is true, this here plus our physical situation requires that we set K is equal to n pi over L for n equals positive integers. I ruled out 0 because that's no wave function. I ruled out all the negative integers because I can't have a negative k. So that's where we ended last class period, is that point. So now let's go forward. This brings us to the title of the class, quantum mechanics. In this particle in a box problem, I haven't had anything quantized. What does it mean to be quantized?
I guess like to have a specific set of numbers that it can be at.
Yeah, only specific values are possible. You can't have continuous values. We didn't start the problem saying only specific values. There was nothing about specific anythings until now. Now we have a quantum condition. This says k can only have certain values. And because k is square root, and I should have this memorized, 2m times energy over h bar squared. Now I have only certain energies allowed. So now I must put an E sub n because n is going to number my energy state. Before I had done it, it wasn't really strictly necessary. It was just a possibility. Now it's necessary because I have different n's that will solve my equation. Hence, I'm going to have different energies that will solve my equation. And so now I'm going to square both sides. And solve for E. So I get E sub n is equal to h bar squared pi squared over 2ml squared times n squared. So now we have our first actual quantum outcome. The energies for particle in the box are quantized. You can only have certain energies. And now we have to just think about this for a second. Like, what kind of sense does that make? That says I put a particle in a box. What's the lowest energy it can have? Now remember, the potential energy is 0, so this E is, in fact, the kinetic energy. What's the lowest energy it can have?
Well, it can't be 0.
Right, it can't be 0. I am pretty sure that I can put a BB in a box and have it stationary. And yet this says I can't. And so you have to start facing the realities here. Am I wrong in my perception, or is the calculation wrong? And what do you suppose the answer is? Do you trust me? The answer is, well, if n is equal to 1, let's say that's an electron in a box that is, let's go with realistic sizes. Let's say that it is a little ball with a mass of 1 gram in a box that's 10 centimeters on the side. Right? We can actually calculate the values then, right? So in that case, now this was a one-dimensional box. Go ahead and make a one-dimensional box for me. I'll sit and watch. So what's the ground state energy? We call the lowest available energy the ground state energy. So let's just calculate this. Hey. Got bored with me or what?
No, it like froze.
Yeah, it froze on our end and stuff.
Yeah, it's kind of weird.
I'm sitting here talking away. Okay, so and I look up and, wait, where did they go? Okay. Everything look normal, or you see my screen?
We don't see your
Yeah,
camera.
you're sure.
Okay. Sure. Cannot use my stylus on this. Good? All right. Okay.
When you mentioned gram within a box of, and then.
Oh, really? I lost you a long time
you were
back.
like this.
Yeah, you were like.
It was awesome, I'm sure. Okay. Then I shall back up just a wee bit. So we're going to say we have a 10 centimeter one-dimensional box. I made a joke there, but I won't repeat. And we put a mass of 1 gram inside that box. And we want to find what is the ground state energy. Doggone it. I thought I clicked out of the box. What's the ground state energy for that particle? Because we want to see if my perception of it being stationary in the box is realistic or not within the quantum calculation. So H bar, what is H bar?
It's really small, right?
It's really small. It's like, well, it's H divided by 2 pi. And since H is 6.266 times 10 to the minus 27. Is that right?
Like that.
Anyway, this is 1.055 times 10 to the, I just realized I'm going to get the exponent wrong. Well, what's the exponent on that? Minus 34?
Yeah.
Units of joules times seconds times pi. I think we're all good with saying just pi squared. Over 2 times 10 to the minus third kilograms times 10 to the minus 2 meters quantity squared. Doing just order of magnitude, pi squared is close to 10. And so this is approximately equal to 10 to the, excuse me?
H bar is squared.
Oh, it's square. Oh, that makes a difference. Yeah. Thank you. So that's going to be 10 to the minus 68. And then we'll add 1 to that. So 10 to the minus 67 on top. Now on the bottom, we have 2 times 10 to the minus 3, 4, 5, 6, 7. So that's going to be about 5 times 10 to the minus 61. And then we've got to do some canceling of units and get joules. 68. Yeah. I think that's right. So that's its kinetic energy. Right, because the potential energy we set V is 0 inside the box. So if that's its kinetic energy, that's 1/2 mass times speed squared. Speed is equal to the square root of 2 times 5, which of course is 10 times 10 to the minus 60, divided by 10 to the minus 3. Ten to the minus 57, the square root of 10 to the minus 57 is along the ballpark of 3 times 10 to the minus 28. So and I could be off. I don't think I am, but I'm not going to be super worried, because what's 1 or 2 times 10 to the minus 28 between friends? Are you going to notice the difference in the ball being stationary in the box and going 3 times 10 to the minus 28 meters per second? Most clearly no. Okay, now I am concerned. Am I right or am I wrong?
I don't know. I'm just trying to see how long it would take it to go 10 centimeters.
Oh.
That's 1 times 10 to the 18.
Yeah, it's going to take a while to cross the box. So the result of this is my perception can't contradict the quantum physics explanation. It still doesn't seem right, because it seems like it should be able to be stationary. But we can establish that my perception would not be able to tell the difference in it being stationary and being in even the 1,000th energy state, right? So there is, in the realm of the physically observable, where you can see it and measure it with a meter stick, there is no difference between being stationary and being in the ground state. It's only in the realm of the microscopic that there's a difference. So that's why people often say that quantum mechanics is the realm of the microscopic, because that's the only time when you actually see the difference. The quantum physics applies at any regime, any size. But why would you ever do a quantum physics calculation to determine the trajectory of a ball when you throw the ball? It'd be a little bit overkill. So, key outcome, we have the energy state. We have multiple energy states. It can have n equals 1, n equals 2, n equals 3. Yes, this here is just going along with what we just did. Everything on this slide we've already done. Now, we need our solutions to have 2 properties, one that we've already talked about. They need to be normalized. But now that we have more than one solution, we have n equals 1, n equals 2, n equals 3, each one of the psi's has to be normalized. So I have psi sub n is equal to b sub n sine of n pi over Lx. That's my solution I have. Now let's just go make sure I'm not being an idiot here. Where did I have it? I had n pi equals, got to go back further. My solution was b sine of kx. And now we found that k is n pi over L. And so if I plug this k in there, that gives me this psi here. Psi is equal to b. Now I said b sub n because I have more than one state. And then I have n pi x over L because I substituted k is equal to n pi over L. So this is my wave function, and it has to be normalized. So I'm going to have to go through and normalize it for every possible n. Of course, we're going to do the normalization calculation in one step and not an infinite number of steps. We'll do it for n as a variable and see what we get. As luck would turn out, in this case, the n doesn't matter. But it could be that n is part of the solution. So we have that. We have the normalization condition. We also have a new one that I have not mentioned, orthogonal. Have you guys come across the word orthogonal?
Yeah, yes.
Okay. Tell me what it means. Okay. Orthogonal is the more than two-dimensional version of perpendicular. Right? We have normal, which is a three-dimensional variation on the term. We have orthogonal, which is n-dimensional. What defines a dimension in my one-dimensional box? Right, this is a one-dimensional box. It had a length L. It didn't have a width It just had a length. So what defines a dimension for that box? Okay, the x is the one dimension that I've been talking about, and it's not the dimension we talk about for the orthogonality. Okay, each psi sub n is, linear algebra speaking, a new dimension. So n was any positive integer. That means I have an infinite dimensional problem here. I have an infinite number of dimensions, each one having to be orthogonal, which is the multidimensional equivalent of perpendicular. So we've got a whole new can of worms to deal with now. How do we enforce orthogonality with an infinite set? This one equation summarizes both orthogonality and normality. So we call it the orthonormal condition. And so let's go through what this means. How comfortable are you guys with the Kronecker delta?
I just learned about it in electrodynamics.
All right. Just for grins,
Being a math background, I have a different use for delta, so.
well, you know the Kronecker delta and the Dirac delta?
Yes. I learned about the Dirac delta in school as well.
Okay. Well, the delta functions are functions that have a simple rule. They're zero for everything except for one situation. And then they're one. And so the Kronecker delta is a discrete delta. So here we have state n and state m, and the Kronecker delta is 0 unless n is equal to m. The Dirac delta is continuous. And so the Dirac delta is written as something like, that's supposed to be a delta, something like that. And the Dirac delta is 0 unless its argument is equal to 0, in which case the Dirac delta is 1. And so usually you have something like Dirac delta of x minus k. Well, let's not use k, let's use a. And that means that the Dirac delta is 0 unless x is equal to a, in which case it's 1. So for today, we're only doing the Kronecker delta, but I wanted to make sure that I don't, you don't just say delta in your head, and then when we get a Dirac delta, you're like, wait, the delta was a different thing. So this Kronecker delta, if m is equal to n, this will give us that, right? And so we have the integral psi sub m star psi sub n dx equals 1 if m equals n. Well, that is our normality condition. That's normalized. Integral over all space of psi star psi is equal to 1. And then we have the second half, integral psi m star psi n dx equals 0 if m is not equal to n. That's our orthogonality. So this one mathematical relation covers both. Now we're going to do this. We're going to normalize each one of our infinite solutions and check to make sure that they are orthogonal. So I will just start with integral. Now I'm integrating over all space. But what is psi if I'm outside of the box? 0. Right. So my integral over all space is effectively going from 0 to L. And I'm just going to put psi n star psi n That has to be 1. That's my normalizing situation. Substitute in what we've just found. Sine is real, so psi star doesn't change anything. So I have to evaluate this integral. The b's are constant, so I can bring out the b mod squared. How do you want to evaluate this?
Integral tables. Yeah.
Integral tables. I put over here how I want to integrate it. If I have sine alpha times sine beta, which in this case I do, it's just alpha is equal to beta, then that's 1/2 cosine of alpha minus beta minus 1/2 cosine of alpha plus beta. So that means that sine of n pi over Lx quantity squared is 1/2 cosine of 0 minus 1/2 cosine of 2n pi over Lx. So I have this. Now this is easier than it appears because I'm going from 0 to L. If I do the integral cosine, if I go from 0 to L, how many, let's say n is equal to 1, how many cycles will I have done going from 0 to L? Because of the 2 n pi, if n is 1, I'll have done 1 complete cycle. I've gone from 0 to 2 pi. And if n is equal to 2, I'll go 0 to 4 pi. And so on. It's always going to be an integer number of cycles. Well, what's the integral of a sinusoid over an integer number of cycles? Spends equal time at the top as it does bottom. 0. So I know that the integral of this is going to be 0. Better write integral is 0. Over integer number of cycles. So that means I'm left with something real simple. That's why I didn't go to the integral table. I wanted to see how it's going to work out. You see, that's the only place n appears. So my result is going to be the same for all n's. And so then finally I have integral of 1/2 from 0 to L is L over 2. So what is the modulus of Bn equal to?
Square root of 2 plus or minus. Well, plus or minus.
Plus or minus. All right. And so we have some variations on what we can choose, but we just choose the real answer, the positive real answer to make life easy, right? Because there's a world of answers I can get. I can put times e to the I theta, where theta is any value I want. It'll still be correct. But we just choose the easy answer and say B sub n is equal to square root of 2 over L. And so we've normalized it. And we've normalized it for all the n's. Well, that was half of it. Now we have to check the orthogonality. So to check orthogonality, I don't know if you guys go through these slides. It seems that it would be a little annoying having to slide further and further to the right. Is that the way you feel about it, or does it matter to you at all?
You get used to it. It's fine. Yeah.
Okay.
I mean, yeah. At times it's a little frustrating, but see, for me, it's frustrating because for some reason my laptop doesn't load the information. So then I'll slide through all the slides, and I'll keep sliding out, and I'll be looking for the information.
And it's over to the right.
After I get to the end, then it loads
Oh.
additional comments.
Oh.
So, yeah.
Well, if you want me to try to organize differently, tell me. I'm malleable. The reason I go to the side is so I work off a slide and I don't get things really out of order by going down and then having stuff beside 3 slides.
Yeah.
So it's normalized. So now we check the orthogonality. So I'm just going to use 1m and n, right? I'm not going to try to do 29 calculations. I'm just going to do the integral, again, 0 to L of psi sub n star psi sub n dx has to be 0. And so just like before, substituting in, now that I have my normalization value, square root 2 over L sine of m pi over Lx, square root 2 over L sine of n pi over Lx dx. I can bring out the 2 over L. And once again, I'll use the same identity that so there I've used that same identity. If m is not equal to n, then this is going to be of some integer, let's just call it and m plus n is going to be another integer. So I can't use k. Okay, then I'll make this alpha and beta. Yeah. Where alpha and beta are both integers. And so now we just have to evaluate what this is going to be if we do the integral. So no square root. It was 2 over L. And then I can factor out a 1/2 from each of these. And so this shouldn't be too hard to do. Integral of cosine is it's positive, isn't it? So it's positive. We are now at the time of checking to see if I'm right or not. What is sine of alpha pi, where alpha is an integer? 0. What is sine of beta pi, where beta is an integer? 0. And of course, sine of 0 is 0. Hence, this whole thing is equal to 0. So we have an orthogonal and a normal, hence orthonormal set of solutions here. You feel super, super accomplished? Yeah. Chris is with me. I don't know about you guys, but I feel like Hannibal, whatever his name is in the A-Team. I love it when a plan comes together. I know what the outcome's supposed to be, but I love it when my math actually works out the way it's supposed to.
That is a good feeling.
All right. So we had, at least for this class, new vocabulary that we've covered here. We had the orthogonality condition. We had orthonormal, which was combining orthogonality and normal. And we used that Kronecker delta. Now the whole slide is selected. That's what that means, just in case you're wondering why it has the circle thing. Another word, complete. Complete means it spans all space. And I'm telling you, if you're not a math major, so Chris is probably like, yeah, that totally makes sense to me. This idea of spanning all space starts to seem really esoteric. I mean, it's an infinite. It was hard enough for me to think about something having an infinite number of dimensions and each one is perpendicular to the others. It's easier for me to put it in my head simply by saying it's not a spatial dimension. It's a dimension for describing a function. But now we have this completeness. It must span all space. What in the dickens does that mean? Well, we can talk about it in three-dimensional space terms and understand what it means, and then just let our minds kind of wander and say, yeah, it must be okay. And when we go to a Hilbert space, an infinite dimensional space. So in 3 dimensions, it's easy to understand. Our 3 dimensions are perpendicular. Up and down is perpendicular to left and right is perpendicular to forward and backward. Yeah, you see I automatically went to that just like Indy did here, you know. That's down to earth to me. And it spans all space because I can describe any point in this room with how far is it in that direction for me, how far is it in that direction for me, and how far is it in that direction for me. I put those together and it will describe exactly one location. There's no ambiguity. There's no different way of describing that location. There's one description. It gets me exactly there. That's what it means to span the entire space. You can use a linear combination of each of those dimensions, 5 meters in this direction, 3 meters in that, and 2 in that, linear combination of them, and get a unique description. There's no other way of describing that one point in space. Now, of course, that was physical space. Now we're talking Hilbert space, an infinite dimensional space that we just kind of wrap our minds around. So that's what completeness means. It means that you have a set of functions that you can use, and any vector can be described as a linear combination of those different individual vectors, in this case, the wave functions. And so that's this right here, this is actually Dirichlet's, oh boy, apparently I pressed a button I didn't mean to. This is Dirichlet's theorem here, that if you look up Dirichlet's theorem, you'll find there's more than one. I spelled it on the next slide in case you want to see how to spell Dirichlet. That you should be able to make any function from taking a linear combination of a complete function. Dirichlet specifically, I think, was talking about PHYS and said that you should be able to take a set of signs, and using those signs, you should be able to make any possible function just by saying this much sine of n pi and this much sine of 2n pi and this much sine of 3n pi, and you should be able to make any function. And then we can take advantage of our orthonormality relation to actually find what these c sub n's are, how much I need for each one. Now I'll start on, my clock's over there in case you're wondering when I look that way. I will start on an application of this because it makes a lot more sense with the application, and we'll continue with that application on Wednesday. But let's just see for sure how these two equations come together. So according to Dirichlet, my function of x should be written as something here. So Dirichlet just says this equation should be true. Now let's use our orthonormal relationship that says the integral of psi m star psi n is equal to, dx is equal to conquer delta of mn. Now, if I do the integral of psi n star f of x dx and plug this function in for f of x, I'm of course going to have an infinite number of integrals. And so I will have, I should have put m here. I will have a summation over n. So there I made the substitution of the function of x. Now the c is a constant, and of course the summation is constant, so I can bring that out. And now you see something kind of cool, right? What do we have for our integral? That's Kronecker delta. So that means that if I do this integral of psi star f of x dx, I have the sum over n c of n Kronecker delta mn, which is then going to be, it's 0 unless m equals n, in which case it's c sub n. And so what I have is this integral here. Notice I have m there, and that's why it's c sub m. Gives me c sub m. So I can find my c sub m's. I can find how much it's in state m by doing this integral. And like I said, it makes a lot more sense. Actually, I won't start it because I only have a minute left in class. So here's where we sit at this point. I used A instead of L here. Different books use different, symbols or, to represent the width of the box. And I use various books as I'm preparing, and I use the nomenclature they use because I'm not thinking. So that's why I have an A here instead of an L. So I will write an L now that I've explained it. So you know that it's technically not an error, but it's an inconsistency. So I wrote the L to make it consistent. So there's our size for all n's. That's every single one of our states. Very beginning, before we did the spatial, we did the temporal solution. Remember, we did it really quick because it was just a simple separate and integrate. And so our complete wave function is going to be a linear combination of these. And so notice I have the n's here. So this is state n for my complete function. So that's telling me both in time and in space, every bit of information we have about the particle. And so we're going to try to now, in the next step, make something useful of it. So here's where we're going to start next class period. We're going to say, let's suppose that I start my system by having a probability distribution given by this function. And then we're going to find what the coefficients are and say, okay, it's this much in this state, this much in this state. The problem is exactly analogous to saying, okay, let's say I pluck a guitar string like this. Now, if I do pluck the guitar string like this, it's going to be probably I start with a state like this instead of the graph of this function is something that looks like this. But it's the same idea. I start it by setting up the system. And with a guitar string, you know the guitar string will resonate at different frequencies. And you're driving a set of frequencies by plucking it here. And if I plucked it here, I drive a different set of frequencies. And so we're doing something analogous to, in fact, since you play the bass guitar, I might go ahead and redo it and do it for, I'm sure it's going to be harder, but do it for something linear like this, just so we can see how it'd work out.
All right.
All right, so I'll see you class Wednesday.